Listening practice, Construction Materials and Measurements. An expanded breakdown of Chapter 1, Introduction to Construction Materials and Measurements, including foundational concepts, practical insights, and learning objectives. Chapter 1, Introduction to Construction Materials and Measurements. Learning objectives, understand the critical role of materials in construction projects. Recognize the importance of precise measurement in ensuring structural integrity and cost efficiency. Identify key standards and codes governing material selection and usage. 1.1 The role of materials in construction, defining construction materials, explanation of materials as the building blocks of infrastructure, e.g., steel, concrete, wood, polymers. Historical evolution, from natural materials, stone, timber, to modern engineered composites. Material selection criteria, functionality, load-bearing versus aesthetic purposes. Cost-effectiveness and availability. Environmental and climatic suitability. Case study, the use of reinforced concrete in skyscrapers versus timber in low-rise sustainable buildings. Failure analysis, the Leaning Tower of Pisa, material limitations in foundation design. 1.2 Importance of accurate measurement in building projects, why measurement matters, impact on structural safety, e.g., improper concrete mix ratios leading to collapse. Cost implications, overestimating or underestimating material quantities. Alignment with design specifications, dimensional tolerances. Measurement fundamentals, units of measurement, metric versus imperial systems. Tools and techniques, from manual tools, tape measures, to digital solutions, BIM software. Real-world example, the Hyatt Regency walkway collapse, 1981. How measurement errors in load calculations led to disaster. 1.3 Overview of material standards and codes, purpose of standards, ensuring quality, consistency, and interoperability of materials. Compliance with safety regulations, e.g., fire resistance, seismic performance. Key organizations and codes, ASTM International, Standards for Steel, Concrete, and Asphalt. ISO, Global Benchmarks for Material Testing and Sustainability. Eurocodes, European Standards for Structural Design. Case study, adoption of ASTM C150 for Portland cement in U.S. infrastructure projects. Challenges in harmonizing international standards for global supply chains. Key takeaways, construction materials define a project's durability, aesthetics, and environmental footprint. Precision in measurement is non-negotiable for safety, efficiency, and regulatory compliance. Standards bridge theory and practice, ensuring materials meet performance expectations. Discussion questions. 1. How might material selection differ between a desert climate and a coastal region? 2. What are the consequences of ignoring measurement tolerances in a high-rise building? 3. Why might a country adopt its own material standards instead of international ones? Further reading, ASTM International Handbook, latest edition. Building Codes illustrated by Francis D. K. Cheng. Materials for Civil and Construction Engineers * by Michael S. Mamluk and John P. Zaniewski. This chapter sets the stage for deeper exploration of materials and measurements, emphasizing their interdependence in achieving successful construction outcomes. Chapter 2, Basic Properties of Construction Materials. Learning objectives, analyze the mechanical, thermal, and electrical properties critical to material performance. Evaluate the environmental impact of construction materials and their role in sustainable design. Apply measurement techniques to assess material properties and compliance with standards. 2.1 Mechanical properties, strength, types, tensile, resistance to stretching, compressive, resistance to crushing, shear, resistance to sliding forces. Measurement, ASTM E8, tensile testing, ASTM C39, concrete compressive strength. Example, high-strength steel in skyscrapers versus masonry in low-rise buildings. Elasticity, Elastic versus plastic deformation, Hooke's law, modulus of elasticity, Young's modulus. Case study, rubber bearings in earthquake-resistant structures to absorb seismic energy. Durability, factors, corrosion, e.g., steel in coastal environments, freeze-thaw cycles, concrete, UV degradation, polymers. Testing, accelerated aging tests, salt spray tests for corrosion resistance. Failure example, the collapse of the Silver Bridge, 1967, due to stress corrosion cracking. 2.2 Thermal and electrical properties, thermal conductivity, importance, insulation materials, e.g., fiberglass, aerogels, for energy efficiency. Measurement, R value, thermal resistance, U value, heat transfer coefficient. Thermal expansion, impact on design, expansion joints in bridges to prevent buckling. Example, aluminum's high thermal expansion in curtain walls. Electrical conductivity, applications, copper wiring versus PVC insulation for electrical safety. Dielectric strength, critical for insulating materials in high voltage environments. Case study, aerogel insulation in NASA's Mars rovers adapted for energy-efficient buildings. 2.3 Environmental impact and sustainability, life cycle assessment, LCA, stages, extraction, production, transportation, use, disposal/recycling. Embodied carbon, CO emissions from material production, e.g., cement accounts for 8% of global emissions. Sustainable practices, recycled materials, fly ash in concrete, reclaimed timber. Certifications, LEED, BREEAM, Cradle to Cradle, C2C. Case study, bamboo flooring versus traditional hardwood, rapid renewability and lower embodied energy. Innovation, cross-laminated timber, CLT, as a carbon-negative alternative to steel and concrete. Key takeaways, mechanical properties dictate structural integrity, thermal/electrical properties influence energy efficiency and safety. Durability testing ensures longevity under environmental stressors. Sustainability requires balancing performance with environmental impact through life cycle thinking. Discussion questions. 1. How does thermal expansion affect material selection in a bridge spanning a desert region with extreme temperature swings? 2. Why might a material with high embodied carbon still be chosen for a project? Consider strength to weight ratios or longevity. 3. Compare the life cycle impacts of concrete versus timber in mid-rise construction. Further reading, The Science and Technology of Civil Engineering Materials by J. Francis Young. Sustainable Construction Materials, ICE Publishing. ASTM Standards, E8, Tensile Testing, C518, Thermal Conductivity. This chapter equips readers to critically assess materials based on their inherent properties and environmental footprint, bridging technical knowledge with sustainable decision-making. Chapter 3, Classification of Construction Materials. Learning objectives, differentiate between natural, synthetic, traditional, modern, sustainable, and recycled materials. Evaluate the advantages, limitations, and applications of each material category. Understand the role of sustainability certifications and life cycle assessments in material selection. 3.1 Natural versus synthetic materials, definitions. Natural materials, sourced directly from nature, e.g., wood, stone, clay. Synthetic materials, engineered or chemically processed, e.g., plastics, composites, concrete. Pros and cons, natural, renewable, biodegradable, but may lack uniformity or durability. Synthetic, customizable for strength/durability, but often energy-intensive to produce. Applications, natural, timber framing in residential homes, stone cladding for aesthetics. Synthetic, fiber-reinforced polymers, FRP, in bridges, PVC piping. Case study, bamboo versus steel, bamboo's tensile strength in sustainable architecture versus steel's versatility in skyscrapers. 3.2 Traditional versus modern materials, definitions, traditional, long-standing use, e.g., adobe, thatch, brick. Modern, innovations enabling advanced engineering, e.g., reinforced concrete, glass facades. Evolution, historical context, mud bricks in ancient Mesopotamia versus steel-framed skyscrapers. Cultural versus functional, traditional materials in heritage restoration versus modern materials for seismic resilience. Case study, The Shard, London, use of modern glass and steel versus traditional masonry in historic London buildings. 3.3 Sustainable and recycled materials, definitions, sustainable, low environmental impact, e.g., bamboo, cork, FSC certified wood. Recycled, repurposed waste, e.g., reclaimed timber, recycled concrete aggregate, post-consumer plastics. Certifications and standards, LEED, BREEAM, Cradle to Cradle, C2C frameworks for assessing sustainability. Life cycle assessment, LCA measuring embodied carbon and energy. Innovations, self-healing concrete, reduces maintenance and extends lifespan. Biodegradable insulation, mycelium-based materials. Case study, Olympic Stadium, Tokyo, use of recycled steel and timber from sustainable sources. Key takeaways, natural and synthetic materials each have unique trade-offs in performance and environmental impact. Modern materials enable architectural innovation but must balance functionality with cultural and ecological considerations. Sustainability requires integrating recycled materials, certifications, and life cycle thinking into design. Discussion questions 1. How might the use of synthetic materials in coastal construction address durability challenges posed by natural materials? 2. Can traditional materials be adapted for modern high-rise buildings without compromising safety? 3. What barriers exist to widespread adoption of recycled materials in the construction industry? Further reading, Cradle to Cradle, Remaking the Way We Make Things by William McDonough and Michael Braungart. The Ecology of Building Materials by B.J.R.N. Berga. FSC Certification Guidelines for Sustainable Forestry. Comparison tables and visual aids, Table 3.1, Natural versus Synthetic Materials, Strength, Cost, Environmental Impact. Timeline, Evolution from Traditional to Modern Materials, 1800s present. Infographic, Life Cycle Stages of Recycled Concrete versus Virgin Concrete. This chapter empowers readers to navigate material classifications with a critical eye, aligning technical requirements with sustainability goals. Chapter 4, Concrete and Cement-Based Materials Learning Objectives, distinguish between types of cement and concrete, including their applications and standards. Understand the role of aggregates, admixtures, and reinforcement in enhancing concrete performance. Apply measurement techniques for slump, strength, and volume to ensure quality control. 4.1 Types of cement and concrete, cement types, Portland cement, ASTM C150 most common type, e.g., type I for general use, type V for sulfate resistance, blended cements, fly ash, type IP, slag cement, type IS, or silica fume for reduced carbon footprint. Specialty cements, white cement, aesthetics, rapid hardening cement, emergency repairs. Concrete types, ready-mix concrete, pre-mixed for consistency in large-scale projects. High-performance concrete, HPC enhanced durability for bridges and skyscrapers. Lightweight concrete, reduced density using expanded shale or perlite, e.g., precast panels. Case study, Three Gorges Dam, China, use of mass concrete with cooling systems to prevent thermal cracking. 4.2 Aggregates, admixtures, and reinforcement, aggregates, coarse aggregates, gravel, crushed stone improve structural strength. Fine aggregates, sand fill voids and enhance workability. Recycled aggregates, crushed concrete from demolition waste. Admixtures, water reducers, plasticizers improve flow without compromising strength, e.g., superplasticizers for self-compacting concrete, retarders/accelerators, adjust setting time, e.g., accelerators for cold weather, air and training agents, enhance freeze-thaw resistance. Reinforcement, rebar, steel bars, ASTM A615, for tensile strength. Fiber reinforcement, steel, glass, or synthetic fibers to reduce cracking. Post-tensioning, high-strength tendons in bridges and parking structures. Case study, Burj Khalifa, Dubai, high-strength concrete, 80 MPa, with microsilica and corrosion-resistant rebar. 4.3 Measurement of concrete slump, strength, and volume, slump test, ASTM C143, procedure, fill a slump cone, remove cone, measure subsidence. Interpretation, low slump, stiff mix for pavements, versus high slump, flowable mix for columns. Strength testing, compressive strength, ASTM C39 cylinder samples tested at 7/28 days. Tensile strength, splitting tensile test, ASTM C496, or flexural strength, ASTM C78. Volume measurement, batching, precise ratios of cement, water, aggregates, e.g., 1:2:3 mix by volume. Yield calculations, compare theoretical versus actual volume to detect errors. Real-world example, Hyatt Regency walkway collapse, 1981. Undetected strength deficiencies in altered concrete supports. Key takeaways, cement and concrete versatility depends on composition, admixtures, and reinforcement. Aggregates and admixtures tailor concrete for specific environments, e.g., freeze-thaw, corrosion. Rigorous testing of slump, strength, and volume ensures compliance and structural safety. Discussion questions. 1. Why might a contractor choose lightweight concrete over conventional concrete for a high-rise facade? 2. How does recycled aggregate affect concrete's mechanical properties compared to virgin aggregate? 3. What risks arise from improper slump measurement during a bridge deck pour? Further reading, Design and Control of Concrete Mixtures, Portland Cement Association. ASTM C94, Ready Mix Concrete Standards. Concrete Microstructure, Properties, and Materials by P. Kumar Mehta. Tables and Visual Aids, Table 4.1, Cement Types and Applications. Diagram, Concrete Batching Process, Cement, Sand, Gravel, Water. Infographic, Slump Test Steps and Interpretation. This chapter bridges material science with practical application, equipping readers to design, test, and deploy cement-based materials effectively in diverse construction scenarios. Chapter 5, Metals in Construction Learning Objectives, identify the types, grades, and structural applications of steel, aluminum, copper, and alloys. Analyze the advantages and limitations of metals in different construction contexts. Apply measurement techniques to assess metal corrosion and thickness for maintenance and safety. 5.1 Steel, Types, Grades, and Applications, Types of Steel, Carbon steel, low cost, high strength, e.g., rebar, structural beams. Alloy steel, enhanced properties, e.g., chromium for corrosion resistance, manganese for toughness. Stainless steel, high corrosion resistance, e.g., AISI 304 for facades, AISI 316 for coastal environments. Structural steel, ASTM A36, general use, ASTM A572, high strength for bridges. Grades and standards, ASTM, USA 992 for wide flange beams, A500 for hollow structural sections, and Europe S235, S355 grades for structural steel. Applications, skyscrapers, steel frames, bridges, weathering steel, pipelines, API 5L steel. Case study, Eiffel Tower, use of wrought iron, precursor to modern steel, and ongoing corrosion management. 5.2 Aluminum, copper, and alloys. Aluminum, properties, lightweight, corrosion resistant, recyclable. Applications, curtain walls, e.g., Burj Al Arab, roofing, aerospace components. Alloys, 6061 T6, structural, 3003, decorative. Copper, properties, high electrical/thermal conductivity, antimicrobial. Applications, electrical wiring, roofing, patented durability, plumbing. Alloys, bronze, statues and marine hardware, saltwater resistance. Brass, decorative fixtures, valves, and gears. Case study, Statue of Liberty, copper skin with steel framework, illustrating galvanic corrosion challenges. 5.3 Measurement techniques for metal corrosion and thickness, corrosion assessment, visual inspection, rust, pitting, or discoloration, ASTM G46. Ultrasonic testing, UT measures thickness loss, ASTM E797. Electrochemical methods, potentiodynamic polarization, ASTM G59, to predict corrosion rates. Thickness measurement, magnetic induction, for coated steel, e.g., pipelines. Eddy current testing, non-destructive evaluation of aluminum and non-ferrous metals. Preventive measures, coatings, galvanization, epoxy, cathodic protection, pipelines, ships. Case study, Golden Gate Bridge, continuous corrosion monitoring and repainting to combat saltwater exposure. Key takeaways, steel dominates structural applications but requires corrosion protection in harsh environments. Aluminum and copper excel in lightweight, electrical, and aesthetic roles but demand alloying for durability. Regular thickness and corrosion measurements are critical for safety, longevity, and cost management. Discussion questions 1. Why might stainless steel be avoided in structural frameworks despite its corrosion resistance? 2. How does aluminum's recyclability align with sustainable construction goals compared to steel? 3. What challenges arise when using copper and steel together in a coastal building? Further reading, Steel Design Handbook, AISC. Aluminum Structures, A Guide to Their Specifications and Design by J. Randolph Kissel. ASTM Standards, E8, Tensile Testing, G1, Corrosion Rate Calculations. Tables and Visual Aids, Table 5.1, Steel Grades and Applications, ASTM vs. N. Infographic, Corrosion Measurement Techniques, Visual, UT, Electrochemical. Case Study Image, Galvanic Corrosion in the Statue of Liberty's Copper-Steel Interface. This chapter equips readers to select, apply, and maintain metals in construction while addressing durability challenges through rigorous measurement and innovation. Chapter 6, Wood and Timber Products Learning Objectives, differentiate between natural timber, hardwoods and softwoods, and engineered wood products. Evaluate the applications, advantages, and limitations of plywood, LVL, and CLT in construction. Apply moisture content measurement techniques to ensure timber quality and durability. 6.1 Natural timber, hardwoods and softwoods. Hardwoods, e.g., oak, maple, teak, properties, dense, durable, and slow-growing, ideal for flooring, furniture, and high-traffic areas. Applications, interior finishes, cabinetry, structural beams in heritage restoration. Softwoods, e.g., pine, cedar, spruce, properties, lightweight, fast-growing, and cost-effective, used for framing, roofing, and temporary structures. Applications, residential framing, decking, and utility poles. Sustainability considerations, certifications, FSC, Forest Stewardship Council, for responsibly sourced timber. Case study, reclaimed hardwood in the restoration of Boston's Old North Church versus plantation-grown pine in modern housing. 6.2 Engineered wood, plywood, LVL, CLT, plywood, manufacturing, cross-laminated veneers bonded with adhesives. Advantages: uniform strength, moisture resistance, marine grade, and versatility. Applications: subfloors, concrete formwork, and shear walls. Laminated veneer lumber, LVL, manufacturing, thin wood veneers glued under pressure for high load-bearing capacity. Advantages: consistent strength, replaces solid timber in beams and headers. Cross-laminated timber, CLT, manufacturing, orthogonal layers of lumber for dimensional stability. Advantages: carbon-negative alternative to steel/concrete, fire-resistant when charred. Case study: Mjøstranet, Norway, 18-story timber tower using CLT for floors and walls, showcasing seismic resilience and sustainability. 6.3 Moisture content measurement and quality assessment, why moisture matters, warping and decay, excess moisture, 19%, promotes fungal growth, too dry, 6%, causes cracking. Standards: ASTM D4442, oven dry method, for precise measurement. Measurement techniques: pin-type moisture meters, penetrate wood surface, ideal for rough lumber. Pinless meters, non-destructive scanning for finished products. Quality grading, visual grading, based on knots, splits, and grain patterns, e.g., FOS grade for hardwoods. Machine grading, stress-rated timber for structural applications, e.g., MSR lumber. Case study: Millennium Tower, London, moisture-related expansion in LVL panels necessitated redesign, highlighting testing oversights. Key takeaways: natural timber, offers aesthetic and structural diversity but requires sustainable sourcing. Engineered wood, enhances strength and sustainability for modern construction. Moisture control, critical to prevent structural failure and extend material lifespan. Discussion questions. 1. Why might CLT be preferred over steel in a carbon-neutral building project despite higher upfront costs? 2. How does reclaimed hardwoods moisture history impact its reuse in new construction? 3. Compare the environmental trade-offs of using plantation-grown softwoods versus tropical hardwoods. Further reading: The Wood Handbook, USDA Forest Products Laboratory. Tall Wood Buildings, Design, Construction, and Performance * by Michael Green. ASTM Standards, D3737, CLT Grading, D1990, Machine Graded Lumber. Tables and Visual Aids, Table 6.1, Hardwood versus Softwood Properties, Density, Durability, Cost. Infographic, CLT Manufacturing Process, Layers, Adhesives, Pressing. Diagram, Moisture Meter Types and Use Cases. This chapter bridges traditional craftsmanship with engineered innovation, empowering professionals to leverage wood's versatility while addressing moisture and sustainability challenges. Chapter 7, Masonry Materials Learning Objectives, identify the types, properties, and applications of bricks, blocks, and stones in masonry construction. Select appropriate mortars and grouts based on structural and environmental requirements. Apply standardized techniques to measure masonry strength and assess joint integrity for quality assurance. 7.1 Bricks, blocks, and stones, bricks, types, clay bricks, burnt, engineering, concrete bricks, and fire-resistant refractory bricks. Manufacturing, extrusion, molding, and firing processes. Key properties include compressive strength, ASTM C67, and water absorption. Applications, load-bearing walls, facades, and paving. Concrete blocks, types, hollow, CMU, for structural walls, solid for foundations, lightweight, aerated, for insulation. Advantages, cost-effective, fire-resistant, and versatile in finishes, split face, scored. Natural stone, types, granite, high strength, limestone, aesthetic, sandstone, weathering resistance. Sustainability, reclaimed stone reduces environmental impact versus quarrying. Case study, the Pantheon, Rome, travertine and brick masonry demonstrating durability over millennia. 7.2 Mortars and grouts, mortar types, ASTM C270, Type N, general purpose, balanced strength and flexibility. Type S, high strength for seismic zones or below-grade applications. Type M, maximum strength, e.g., retaining walls. Lime mortar, historic restoration, flexible, breathable. Grout, purpose, fills voids in reinforced masonry, high-flow mixes for deep cavities. Composition, cementitious or epoxy-based for chemical resistance. Additives, plasticizers, improve workability. Air entrainers, freeze-thaw resistance in cold climates. Failure example, Venice's subsidence, saltwater degradation of mortar in historic buildings. 7.3 Measuring masonry strength and joint integrity, compressive strength testing, prism test, ASTM C1314 masonry assemblies tested under load to simulate real-world conditions. Unit strength method, correlates brick/block strength to wall strength. Non-destructive evaluation, ultrasonic pulse velocity, UPV detects internal voids or cracks. Rebound hammer, ASTM C805 estimates surface hardness. Joint integrity, visual inspection, cracks, efflorescence, or spalling. Bond wrench test, ASTM C1072 measures flexural bond strength of mortar. Infrared thermography, identifies moisture intrusion in joints. Case study, London's Grenfell Tower, mortar joint failures in cladding contributing to fire spread. Key takeaways, material choice, bricks offer aesthetics, blocks provide structural efficiency, and stone ensures longevity. Mortar/grout compatibility, critical for load transfer and environmental resilience. Testing protocols, ensure compliance with safety standards and prevent catastrophic failures. Discussion questions 1. Why might Type S mortar be preferred over Type N in a coastal region with high humidity? 2. How does reclaimed stone's porosity affect its performance in modern masonry compared to newly quarried stone? 3. What are the risks of using non-compliant grout in a reinforced masonry wall? Further reading, Masonry Design and Detailing by Christine Bell. ASTM C140, Sampling and Testing Concrete Masonry Units. The Art of the Stonemason by Ian Cramb. Tables and Visual Aids, Table 7.1, Mortar Types and Applications, ASTM C270. Infographic, Steps in Prism Testing, Assembly, Curing, Load Application. Case Study Image, Efflorescence Patterns indicating moisture issues in brickwork. This chapter bridges historical craftsmanship with modern engineering, equipping professionals to design, evaluate, and maintain masonry structures with an emphasis on durability and sustainability. Chapter 8, Polymers and Composite Materials Learning Objectives, understand the composition, properties, and applications of plastics, PVC, and fiber-reinforced polymers, FRP, in construction. Evaluate the use of polymers in insulation and structural components, balancing performance with environmental considerations. Apply standardized testing methods to assess the durability and longevity of composite materials. 8.1 Plastics, PVC, and fiber-reinforced polymers, FRP, plastics, types, thermoplastics, e.g., polyethylene, PVC, versus thermosets, e.g., epoxy, polyester. Properties, lightweight, corrosion resistant, and moldable, limited fire resistance and susceptibility to UV degradation. PVC, polyvinyl chloride, applications, plumbing pipes, window frames, electrical insulation. Challenges, brittleness at low temperatures, phthalate additives raise environmental concerns. Fiber-reinforced polymers, FRP, composition, polymer matrix, epoxy, vinyl ester, plus reinforcing fibers, glass, carbon, aramid. Advantages: high strength to weight ratio, corrosion resistance, fatigue performance. Case study: FRP rebar replaces steel in concrete bridges to prevent corrosion in coastal environments. 8.2 Applications in insulation and structural components. Insulation, expanded polystyrene, EPS rigid foam boards for walls and roofs. Polyurethane foam, spray applied for air sealing and thermal efficiency. Structural components, FRP bridge decks, lightweight alternative to steel/concrete, e.g., Michigan's FRP reinrated bridges. Composite panels, glass fiber reinforced panels, GFRP, for facades and cladding. 3D printed polymers, custom architectural elements using ABS or PLA filaments. Sustainability considerations, recyclability, challenges with thermoset composites, emerging chemical recycling techniques. Biodegradable polymers, PLA in temporary formwork or non-load-bearing applications. 8.3 Testing composite material durability, key tests and standards, tensile strength, ASTM D638 measures stress-strain behavior of plastics. Impact resistance, ASTM D256 Charpy/ISA tests for toughness. Environmental exposure, UV resistance, ASTM G154 accelerated weathering to simulate sunlight degradation. Moisture absorption, ASTM D570 evaluates swelling and hydrolysis in composites. Fire performance, ASTM E84 flame spread and smoke density ratings. Advanced techniques, thermogravimetric analysis, TGA assesses thermal stability. Scanning electron microscopy, SEM detects fiber matrix delamination. Case study, London's Crossrail project, FRP used in tunnel linings, rigorous testing for fire and moisture resistance. Key takeaways, material selection, polymers offer versatility but require additives, e.g., UV stabilizers, flame retardants, for harsh environments. FRP innovation, enables lightweight, corrosion-free structures but faces recycling challenges. Durability testing, critical to predict lifespan and prevent failures like delamination or creep. Discussion questions 1. Why might FRP be preferred over steel in a chemical plant's structural components? 2. How does the recyclability of thermoplastics compare to thermosets, and what innovations address this gap? 3. What trade-offs exist between using EPS insulation and natural materials like cellulose? Further reading, Composite Materials, Science and Engineering by Krishan K. Chawla. Plastics in Construction, A Practical Guide by Brian J. Smith. ASTM Standards, D3039, FRP Tensile Testing, E662, Smoke Density. Tables and Visual Aids, Table 8.1, Polymer Types and Applications, Thermoplastics versus Thermosets. Infographic, FRP Manufacturing Process, Fiber Layup, Resin Infusion, Curing. Case Study Image, UV Degradation Comparison between coated and uncoated PVC. This chapter equips readers to leverage polymers and composites in modern construction while addressing durability, safety, and sustainability through rigorous testing and innovative design. Chapter 9, Asphalt and Bituminous Materials Learning Objectives, understand the composition, types, and mix design principles of asphalt and bituminous materials for pavements. Analyze the role of viscosity and density in determining asphalt performance and durability. Apply standardized testing methods to ensure quality control in asphalt production and placement. 9.1 Pavement Materials and Mix Design, Asphalt Types, Hot Mix Asphalt, HMA High Temperature Production for Highways and Heavy Traffic. Warm Mix Asphalt, WMA, Reduced Energy Use with Additives, e.g., wax, foaming, for lower emissions. Cold Mix Asphalt, Ambient Temperature Application for Pothole Repairs and Rural Roads. Bituminous binders, penetration grade, e.g., Pen 60/70 measures hardness, higher grades for colder climates, performance grade, PG tailored to temperature ranges, e.g., PG 64 to 22 for moderate climates, mixed design, superpave system, aggregate selection, gradation, angularity, and durability, ASTM D6926. Binder aggregate ratio, optimized for stability, flexibility, and resistance to rutting. Performance testing, Marshall stability test, ASTM D6927 load resistance under traffic. Dynamic modulus test, evaluates stiffness under varying temperatures and loads. Case study, I-35W Bridge, Minneapolis, use of high-performance asphalt mixes to reduce thermal cracking in extreme climates. 9.2 Measurement of viscosity and density. Viscosity, importance, determines workability during mixing and compaction. Measurement tools, Brookfield viscometer, ASTM D4402 rotational spindle for bitumen flow. Penetration test, ASTM D5 depth. The needle sinks into asphalt under load. Density, field measurement, nuclear density gauge, ASTM D2950 non-destructive in situ testing. Core sampling, ASTM D5361 lab analysis for air void content. Impact on durability, low density equals high air voids, water infiltration and raveling. High density equals insufficient voids, bleeding and rutting. Quality control, job mix formula, JMF ensures compliance with designed viscosity and density. Case study, Denver International Airport runway, precision density testing to prevent premature wear under heavy aircraft loads. Key takeaways, asphalt mix design balances aggregate properties, binder performance, and environmental conditions. Viscosity governs application ease, while density directly impacts pavement longevity. Sustainability innovations, e.g., WMA, recycled asphalt pavement/wrap, reduce carbon footprint. Discussion questions. 1. Why might WMA be preferred over HMA in urban areas despite lower initial strength? 2. How does aggregate gradation influence the viscosity of an asphalt mix during compaction? 3. What risks arise from failing to meet air void specifications in asphalt density? Further reading, The Asphalt Handbook, MS4, Asphalt Institute. Pavement Analysis and Design by Yang H. Huang. ASTM Standards, D6373, Performance Graded Asphalt Binder, D6857, Dynamic Modulus. Tables and Visual Aids, Table 9.1, Asphalt Types and Applications, HMA versus WMA versus Cold Mix. Infographic, Superpave Mix Design Process, Aggregate Selection, Binder Testing, Compaction. Case Study Image, Nuclear Density Gauge in use during highway construction. This chapter equips engineers and contractors to design, test, and deploy asphalt pavements with precision, emphasizing the interplay between material science, environmental sustainability, and rigorous quality control. Chapter 10, Glass and Ceramics Learning Objectives, identify key types of architectural glass and their applications in modern construction. Evaluate the properties and uses of ceramic tiles and fire-resistant materials. Apply measurement techniques to assess optical and thermal performance in building design. 10.1 Types of architectural glass, float glass, production, molten glass floated on tin for uniform thickness. Applications, windows, mirrors, and base for other glass types. Tempered glass, process, thermally treated to enhance strength, shatters into blunt pieces. Uses, skylights, shower doors, and facades in high-impact zones. Laminated glass, structure, sandwiched PVB interlayer for safety and sound dampening. Applications, hurricane-resistant windows, bridges, and acoustic barriers. Insulated glass units, EGUS, design, double/triple glazing with argon gas for thermal insulation. Uses, energy-efficient buildings, cold climates. Low emissivity, low E, glass, coating, metallic layer to reflect infrared radiation. Benefits: reduces energy loss, used in green buildings like The Edge, Amsterdam. 10.2 Ceramic tiles and fire-resistant materials. Ceramic tiles, types, porcelain, dense, low porosity, versus non-porcelain, glazed for moisture resistance. Applications: flooring, cladding, e.g., Barcelona Pavilion's iconic use. Fire-resistant ceramics, materials, refractory ceramics, alumina, silica, for high-temperature stability. Uses: fireplace linings, industrial kilns, fireproof building panels. Case study: One World Trade Center, fire-resistant ceramic fiber insulation in structural elements for enhanced safety. 10.3 Optical and thermal performance measurement, optical properties, visible transmittance, VT measures light passage, ASTM D1003. Glare reduction, tinted or frosted glass for office environments. UV blocking, laminated glass to protect interiors from sun damage. Thermal properties, U value, heat transfer coefficient, lower equals better insulation. Solar heat gain coefficient, SHGC fraction of solar radiation emitted, ASHRAE standards. Testing tools, spectrophotometers, analyze light transmission/reflection. Heat flow meters, measure thermal conductivity, ASTM C518. Case study: Bullitt Center, Seattle, triple glazed Agus with low E coatings achieving net zero energy use. Key takeaways: glass diversity, from tempered safety glass to energy saving low E variants, tailored for safety, aesthetics, and efficiency. Ceramic versatility, combines durability, tiles, with life-saving fire resistance, refractory materials. Performance metrics, optical/thermal measurements are critical for compliance with energy codes and occupant comfort. Discussion questions. 1. Compare the suitability of laminated versus tempered glass for a coastal high-rise facing hurricane risks. 2. How do refractory ceramics enhance safety in industrial versus residential settings? 3. Why might a designer prioritize SHGC over U value in a tropical climate? Further reading, Architectural Glass to Resist Seismic and Extreme Climatic Events by Matthias Haldeman. Ceramic Materials, Science and Engineering by C. Barry Carter and M. Grant Norton. Standards, ASTM E2141, Window UV Durability, ISO 10292, Thermal Calculations. Visual aids, diagram, laminated glass layers and impact resistance mechanism. Table, comparison of ceramic tile types, water absorption, strength, uses. Infographic, thermal performance metrics, U value, SHGC, in building envelopes. This chapter bridges material innovation and practical application, empowering architects and engineers to leverage glass and ceramics for safety, sustainability, and aesthetic excellence. Chapter 11, Units and Systems of Measurement. Learning objectives, differentiate between metric and imperial measurement systems and their global usage in construction. Apply dimensional tolerances and conversion techniques to ensure accuracy in design and execution. Navigate challenges of unit standardization in multinational projects. 11.1 Metric versus imperial systems, historical context. Metric system, developed during the French Revolution, based on decimal units, meters, liters, kilograms. Imperial system, originated in Britain, uses feet, inches, pounds, and gallons. Global usage, metric, standard in most countries, EU, Asia, Africa, and scientific communities. Imperial, predominant in the US, Liberia, and Myanmar, hybrid use in the UK and Canada. Construction challenges, miscommunication, errors in multinational projects, e.g., Airbus A380 parts mismatched due to inch/mm confusion. Industry preferences, metric, preferred for precision in engineering and modular design. Imperial, common in U.S. residential construction, e.g., 16 stud spacing. 11.2 Dimensional tolerances and conversions. Tolerances, definition, permissible limits of variation in physical dimensions, e.g., plus or minus 2 mm for steel beams. Standards, ISO 2768, general tolerances for linear and angular dimensions. ASME Y14.5, geometric dimensioning and tolerancing, GD&T, in the U.S., impact, over-tolerance in concrete slab thickness can compromise structural integrity. Conversions, key formulas, length, 1 inch equals 25.4 mm, 1 foot equals 0.3048 meters. Area, 1 square foot equals 0.0929 square meters. Weight, 1 pound equals 0.4536 kilograms. Tools, software, AutoCAD unit settings, BIM software, Revit, ArchiCAD. Manual checks, double-check conversions for critical components, e.g., rebar spacing. Case study, Mars Climate Orbiter failure, 1999 $125 million loss due to imperial/metric unit mix-up in thruster software. Key takeaways, system compatibility, metrics decimal base simplifies calculations, while imperial persists in legacy systems. Tolerance adherence, ensures components fit and function as designed, e.g., prefab modular buildings. Conversion vigilance, errors can lead to costly rework, delays, or safety risks. Discussion questions 1. Why might a U.S. firm working on a Middle Eastern project face challenges adopting metric units? 2. How do dimensional tolerances affect the assembly of prefabricated steel structures? 3. What strategies can mitigate unit conversion errors in international supply chains? Further reading, Metric Handbook, Planning and Design Data by David Littlefield. Engineering Design with SolidWorks by David Blanchard, Unit Management in CAD. Standards, ISO 8015, Geometric Tolerancing, NIST SP 811, Unit Conversion Guidelines. Visual aids, Table 11.1, Common metric/imperial conversions, length, area, volume, weight. Infographic, tolerance ranges for common materials, steel, concrete, timber. Case study image, Mars Climate Orbiter's trajectory error due to unit mismatch. This chapter equips professionals to navigate measurement systems and tolerances with precision, ensuring seamless collaboration and compliance in global construction projects. Chapter 12, Tools for Construction Measurement Learning Objectives, compare traditional and advanced tools for construction measurement, including their applications and limitations. Evaluate the role of 3D scanning and BIM integration in improving accuracy and efficiency. Apply best practices for selecting and calibrating measurement tools in diverse project contexts. 12.1 Calipers, tape measures, and laser distance tools, calipers, types, vernier, dial, and digital calipers. Applications, precision measurement of rebar thickness, pipe diameters, or joint gaps. Standards, ASTM E18, material testing, for accuracy, plus or minus 0.02 mm. Tape measures, types, steel tapes, long distance, fiberglass tapes, flexible, non-conductive. Best practices, tension control, avoiding sag over long spans, and regular calibration. Case study, misalignment in timber framing due to a stretched tape measure, causing structural instability. Laser distance measures, advantages, speed, long range, up to 250 meters, and minimal human error. Limitations, accuracy, plus or minus 1.5 mm, affected by reflective surfaces or bright sunlight. Applications, site surveys, rough grading, and interior layout. 12.2 Advanced Tools, 3D Scanners and BIM Integration, 3D Laser Scanners, Types, Time of Flight, Phase Shift, and Structured Light Scanners. Applications, as-built models, capturing existing conditions for retrofits, e.g., historic renovations. Quality control, comparing scanned data to BIM models for deviations. Case study, Sydney Opera House restoration, 3D scanning to map cracks and deformations in concrete shells. BIM integration, workflow, scanned data point clouds BIM software, Revit, AutoCAD, for clash detection and updates. Benefits, real-time collaboration across disciplines, architecture, MEP, structural. Reduced rework by identifying conflicts early, e.g., ductwork interfering with beams. Standards, ISO 19650, BIM data management, and COBie, construction operations data. Emerging tools, drones with LiDAR, topographic mapping and volumetric calculations. Augmented reality, AR overlaying BIM models on-site for alignment checks. Key takeaways, traditional tools, essential for quick, on-site measurements but prone to human error. Advanced tools, enable millimeter precision and digital collaboration but require training and investment. BIM synergy, transforms raw data into actionable insights, driving efficiency in complex projects. Discussion questions 1. Why might a contractor choose a laser measure over a tape measure for a high-rise curtain wall installation? 2. How does 3D scanning reduce risks in renovating aging infrastructure compared to manual surveys? 3. What barriers prevent small firms from adopting BIM integrated measurement tools? Further reading, Construction Laser Handbook by Herbert L. Nichols. BIM for Dummies by Stefan Mordu and David Philp. Standards, ASTM E2544, 3D scanning, ISO 16757, BIM data structures. Visual aids, Table 12.1, tool comparison, accuracy, range, cost. Infographic, BIM workflow from 3D scan to clash detection. Case study image, point cloud model of a scanned industrial facility. This chapter bridges manual craftsmanship with cutting-edge technology, empowering professionals to select tools that balance precision, speed, and cost in an evolving construction landscape. Chapter 13, Quantity Takeoff and Estimation Learning Objectives, Master Methods for Calculating Material Quantities for Construction Projects. Utilize software tools to streamline cost estimation and reduce human error. Analyze the impact of accurate takeoffs on budgeting, procurement, and project timelines. 13.1 Calculating Material Quantities for Projects, Quantity Takeoff Fundamentals, Definition, Measuring materials, e.g., concrete volume, steel tonnage, lumber board feet, from drawings/specifications. Methods, manual takeoffs, scaling from blueprints, using formulas, e.g., concrete volume equals length times width times depth. Digital takeoffs, PDF markups, on-screen measurements, e.g., Bluebeam Rev. Best practices, cross-referencing architectural, structural, and MEP drawings. Including waste factors, e.g., 10% for lumber cuts, 5% for concrete. Common pitfalls, scope gaps, missing hidden elements, e.g., reinforcement in footings. Unit errors, confusing lineal feet versus square feet, e.g., flooring materials. Case study, Denver Airport Baggage System, underestimated conveyor belt quantities led to delays and $2 billion cost overruns. 13.2 Software Tools for Cost Estimation, Key Features of Estimation Software, Database Integration, RS Means, Craftsman Books for Unit Costs. OCR, Optical Character Recognition Auto-Extract Quantities from Scanned Plans. Cloud Collaboration, Real-Time Updates for Teams. Popular Tools, Bluebeam Rev. Strengths, PDF-based takeoffs, customizable tool sets, markup tracking. Use case, electrical contractor estimating conduit lengths from PDF plans. PlanSwift, strengths, drag and drop assemblies, e.g., walls, Roofs, labor cost integration. Use case, subcontractor calculating drywall quantities for a hospital. Cost X, BIM integrated takeoffs from 3D models. Autodesk Takeoff, AI-driven measurement for earthwork and MEP systems. BIM integration, automated quantities, extract data directly from Revit/Navisworks models. 5D estimation, linking 3D models with cost, 4D equals time, 5D equals cost. Case study, HS2 Railway, UK, BIM-based quantity takeoffs reduced estimation time by 30% across 25 contractors. Key takeaways, accuracy first, errors in takeoffs cascade into budget overruns and delays. Tool selection, match software to project complexity, e.g., PlanSwift for residential, Cost X for infrastructure. Human and tech synergy, software augments but doesn't replace expert judgment. Discussion questions 1. How might a contractor transition from manual to digital takeoffs without disrupting workflows? 2. What challenges arise when estimating quantities for retrofit projects with incomplete as-built drawings? 3. Can over-reliance on software lead to ethical issues, e.g., ignoring site-specific risks? Further reading, Construction Estimating Using Excel by Stephen Peterson. RS means Construction Cost Data, Annual Editions. Standards, CSI Master Format for Organizing Cost Codes. Visual Aids, Table 13.1, Software Comparison, Bluebeam vs PlanSwift vs Cost X. Infographic, Steps in a Digital Takeoff Process, Upload plans, measure areas, generate reports. Case Study Image, BIM model highlighting quantified structural steel elements. This chapter equips estimators, contractors, and project managers to balance precision and efficiency, leveraging both traditional techniques and digital innovation to control costs and mitigate risks. Chapter 14, Quality Control and Testing Learning Objectives, understand the principles and applications of non-destructive testing, NDT, methods in construction. Evaluate the role of sampling and laboratory analysis in ensuring material compliance and structural integrity. Implement best practices for quality assurance across construction phases to mitigate risks. 14.1 Non-destructive testing, NDT, methods, definition, techniques to evaluate materials, components, or systems without causing damage. Common NDT methods, ultrasonic testing, UT, principle, high-frequency sound waves detect internal flaws, e.g., cracks in welds. Standards, ASTM E164, weld inspection, ISO 17640, wall thickness measurement. Radiographic testing, RT, principle, X-rays or gamma rays reveal subsurface defects, e.g., voids in concrete. Applications, pipeline welding, bridge girders. Magnetic particle testing, MT, principle, detects surface/near surface flaws in ferromagnetic materials, e.g., steel beams. Ground penetrating radar, GPR, principle, electromagnetic waves map rebar location, voids, or delamination in concrete. Case study, Millennium Tower, San Francisco, GPR used to assess foundation deficiencies causing tilt. Infrared thermography, applications, detects moisture intrusion, insulation gaps, or energy leaks in building envelopes. Advantages, preserves structural integrity, cost-effective for large-scale projects. Limitations, requires skilled technicians, limited depth resolution in some methods. 14.2 Sampling and laboratory analysis, sampling protocols, random sampling, ensures statistical representation, e.g., concrete cores from different slab sections. Stratified sampling, targets specific areas, e.g., joints in pavements. Standards, ASTM C172, fresh concrete sampling, ACI 318, reinforcement testing. Laboratory tests, compressive strength, concrete cylinders tested at 7/28 days, ASTM C39. Chemical analysis, X-ray fluorescence, XRF, to verify steel alloy composition. Durability testing, chloride permeability, ASTM C1202 measures concrete's resistance to corrosion. Freeze-thaw resistance, ASTM C666 evaluates degradation in cold climates. Fire resistance, furnace testing for materials like gypsum boards or fireproof coatings, ASTM E119. Case study, Champlain Towers collapse, 2021 inadequate sampling/testing of corroded rebar and spalling concrete. Key takeaways, NDT versus destructive testing. NDT saves time/resources but may require lab validation for critical components. Sampling rigor, proper techniques prevent biased results and ensure compliance with specs. Ethical responsibility, tampering with test results or ignoring anomalies risks catastrophic failures. Discussion questions 1. Why might UT be preferred over RT for inspecting welds in a densely populated urban area? 2. How does improper sampling affect the reliability of laboratory test results? 3. What ethical dilemmas arise when test results conflict with project deadlines? Further reading, Non-Destructive Evaluation of Materials by Javed Hashimi. Construction Materials, Their Nature and Behavior by Peter Dominy and John Ilston. Standards, ASTM E1444, MT, ISO 9712, NDT Personnel Certification. Visual aids, Table 14.1, NDT Methods Comparison, Cost, Accuracy, Depth Penetration. Infographic, Steps in Concrete Sampling and Testing, Field Lab Report. Case Study Image, GPR Scan showing rebar corrosion in a parking garage slab. This chapter prepares engineers, inspectors, and project managers to deploy NDT and lab analysis effectively, ensuring materials meet design intent while upholding safety and regulatory standards. Chapter 15, Measurement Standards and Compliance Learning Objectives. Understand the roles of ISO, ASTM, and EN standards in construction materials and measurement. Analyze how building codes integrate these standards to ensure safety and quality. Implement strategies to ensure compliance with international and regional standards. 15.1 ISO, ASTM, and EN Standards 1. ISO Standards, Global Reach, develops universally accepted standards, e.g., ISO 9001 for quality management, ISO 14001 for environmental practices. Material-specific examples, ISO 10406, testing of fiber-reinforced polymer, FRP, composites. ISO 1920, concrete testing for strength and durability. 2. ASTM International, material and method focus, ASTM C39, compressive strength testing of concrete. ASTM A36, carbon steel for structural applications. Testing protocols, standards for non-destructive testing, NDT, corrosion resistance and fire safety. 3N, Euronorm, standards, European integration, harmonized across EU member states, e.g., N 1992 for concrete design, N 10025 for structural steel. National annexes, local adaptations, e.g., UK's NA to N 1990 for load calculations. 15.2 Ensuring compliance with building codes 1. Code standard synergy, direct references, building codes, e.g., IBC, Eurocodes, site standards for material properties, testing, and design. Example, IBC Chapter 19 mandates ASTM C150 cement for structural concrete. Certifications, third-party verification, e.g., UL, CE marking, to confirm compliance. 2. Documentation and audits, material test reports, MTRs essential for steel, concrete, and polymers to validate compliance. Digital tools, BIM software flags non-compliant materials during design, e.g., Revit alerts for N1990 conflicts. 3 Challenges in compliance, conflicting standards, global projects may face clashes, e.g., ASTM versus N steel grades, equivalence assessments required. Regulatory updates, tracking revisions, e.g., 2023 updates to ISO 45001 for occupational safety. 15.3 Case Studies 1. Failure Case, Hyatt Regency Walkway Collapse, 1981, Cause, Non-compliant steel box beams, ASTM A36 deviations, and design changes. Lesson, rigorous adherence to ASTM standards prevents catastrophic failures. 2 Success Case, Crossrail Project, London, Strategy, N 1990, Compliance for tunnel linings and BIM integration for real-time audits. Outcome, on-time delivery with 0 major compliance breaches. 15.4 Best Practices for Compliance, Pre-construction, Specification Reviews, align material specs with ASTM/ISO/N and local codes. Training, certify teams on standards, e.g., ACI certification for concrete testing. During construction, sampling and testing, follow ASTM D3665 for random sampling of road materials. Digital compliance tools, Bluebeam Review for automated quantity takeoffs against standards. Post-construction, audits, ISO 19011 guidelines for quality management system audits. Key takeaways, standards as backbone, ISO, ASTM, and N provide the technical basis for safe, durable structures. Dynamic compliance, requires continuous education, documentation, and adaptation to evolving codes. Global versus local, balance international standards with regional amendments, e.g., Eurocode's national annexes. Discussion questions 1. How might a contractor resolve a conflict between ASTM and N standards in AU.SEU joint venture? 2. What risks arise when outdated standards are referenced in building codes? 3. How can digital tools streamline compliance in megaprojects? Further reading, ISO Standards in Construction, ISO Publications. ASTM Annual Book of Standards, Volume 04.02, Concrete and Aggregates. Eurocode 2, Design of Concrete Structures, N 1992. Visual Aids, Table 15.1, Key Standards Crosswalk, ISO versus ASTM versus N. Infographic, Compliance Workflow, Design Procurement Construction Audit. Case Study Image, CE Marking on Structural Steel for EU Compliance. This chapter equips professionals to navigate the complex landscape of standards and codes, ensuring projects meet global benchmarks while adhering to local regulations. Chapter 16, Material Selection for Different Climates. Learning Objectives, evaluate material performance in extreme cold, hot, humid, and coastal environments. Select materials based on thermal, durability, and sustainability criteria. Apply standards and testing protocols to ensure climate resilience. 16.1 Cold versus hot environments. Cold climates, e.g., Alaska, Scandinavia, key challenges, freeze-thaw cycles, thermal contraction, and ice/snow loads, material considerations, concrete, air-entrained mixes, ASTM C666 compliance, to prevent cracking. Metals, low-temperature toughness, e.g., ASTM A709 grade 50W steel for bridges. Insulation, high R-value materials, spray foam, fiberglass, to minimize heat loss. Case study, Svalbard Global Seed Vault, Norway, reinforced concrete with waterproofing and thermal buffers to withstand 18 degrees Celsius. Hot climates, e.g., Dubai, Arizona, key challenges, UV degradation, thermal expansion and heat retention, material considerations, roofing, reflective clay tiles or cool roofing membranes, ASTM C1549 for solar reflectance. Metals, expansion joints in steel frameworks, anodized aluminum for UV resistance. Polymers, UV stabilized PVC or composites to prevent brittleness. Case study, Burj Khalifa, Dubai, double glazed low-E glass and terracotta cladding for thermal regulation. 16.2 Humidity and coastal area considerations. Humid environments, e.g., Singapore, Florida, key challenges, mold growth, wood rot, and corrosion. Material considerations, wood, pressure-treated lumber or tropical hardwoods, e.g., teak, with natural rot resistance. Metals, stainless steel, AISI 316, or galvanized steel for corrosion resistance. Coatings, antimicrobial paints and vapor barriers, ASTM E96 for moisture permeability. Coastal zones, e.g., Miami, Sydney, key challenges, salt spray, chloride ingress and tidal flooding. Material considerations, concrete, high-density mixes with epoxy-coated rebar, ASTM A775, to resist chloride penetration. Composites, fiber-reinforced polymers, FRP, for docks and seawalls. Case study, Sydney Opera House, marine-grade stainless steel and hydrophobic sealants to combat saltwater erosion. Sustainability and life cycle considerations, cold climates, insulation materials with low embodied carbon, e.g., cellulose, to reduce heating demands. Hot climates, light-colored, reflective surfaces to lower urban heat island effects. Coastal/humid, durable materials, e.g., recycled plastic lumber, to minimize replacement cycles. Standards and testing, freeze-thaw resistance, ASTM C666, concrete, ISO 16770, plastics. Corrosion testing, ASTM B117, salt spray, ASTM G48, pitting resistance. Thermal performance, ISO 6946, insulation, ASTM D4804, UV stability. Discussion questions. 1. How does material selection for a coastal high-rise differ from a desert skyscraper? 2. Why might recycled materials face limitations in extreme climates without additional treatments? 3. How can digital tools, e.g., BIM, simulate climate impacts on material performance during design? Further reading, Building in Extreme Environments by Ken Hayes. Coastal Construction Manual, FEMA P55. Standards, ASTM E2556, Water Penetration Testing, and January 5, 1991, Thermal Actions. Visual aids, Table 16.1, Material Performance Matrix, Cold versus Hot versus Coastal. Infographic, Life Cycle Stages of Materials in a Hurricane-Prone Coastal Building. Case Study Image, Cross-section of Svalbard seed vault showing insulation layers. This chapter empowers architects and engineers to make informed, climate-responsive material choices, balancing durability, efficiency, and sustainability in a rapidly changing world. Case Studies in Material Measurement. 1. High-rise building, steel and concrete quantities overview. High-rise buildings require precise material estimation to ensure structural integrity, cost efficiency, and compliance with safety standards. Steel and concrete are the primary materials used. Key measurements and considerations: concrete, measured in cubic meters, m superscript 3, for foundations, columns, beams, and slabs. Example, a 50-story building may require 30,000 m superscript 3 of concrete. Factors affecting quantity: slab thickness, column spacing, seismic requirements. Steel reinforcement, rebar, measured in tons or kilograms per cubic meter of concrete, kg/m superscript 3. Typical range, 100-150 kg/m superscript 3 for high rises. Example, 30,000 cubic meters of concrete times 120 kg/m superscript 3 equals 3,600 tons of rebar. Structural steel, beams, columns, measured in tons, often 30-50 kg/m superscript 2 of floor area. Example, A 50,000 square meters floor area times 40 kg/m superscript 2 equals 2,000 tons of steel. Challenges: overestimation leads to higher costs, underestimation causes delays. Waste management: 5–10% excess material typically ordered. 2. Sustainable housing, timber and recycled materials overview. Sustainable housing prioritizes low-carbon materials like timber and recycled content to reduce environmental impact. Key measurements and considerations: engineered timber, CLT, GLM, measured in cubic meters, m superscript 3, or board feet. Example: a 150 square meters house may use 30 m superscript 3 of CLT. Benefits: carbon sequestration, lighter than concrete/steel. Recycled materials: steel, concrete, insulation. Recycled steel, 90% less energy than virgin steel. Crushed recycled concrete, used as aggregate, measured in tons. Example: a sustainable home may use 20–30% recycled content. Challenges: availability and cost of certified sustainable timber. Structural limits of recycled materials in load-bearing applications. Comparison: material high-rise, steel/concrete, sustainable housing, timber/recycled, primary use load-bearing frames, cores, walls, floors, insulation measurement tons, steel, m superscript 3, concrete, m superscript 3, timber, percent recycled content. Carbon impact: high, 1 ton steel 1.8 ton CO, low/negative, timber stores carbon. Conclusion: high-rises rely on bulk steel/concrete with precise tonnage/m superscript 3 tracking. Sustainable housing focuses on renewable/recycled materials, measured by volume and eco certifications. Would you like additional details on specific calculation methods or sustainability certifications? Case studies in material measurement. 18. Errors and adjustments in measurement. Accurate material measurement is critical in construction to prevent cost overruns, delays, and structural issues. However, errors can occur due to estimation mistakes, measurement inaccuracies, or calibration failures. Below are common errors and methods for adjustments. 1. Common mistakes in material estimation. A high-rise buildings, steel and concrete. 1. Incorrect volume calculations. Mistake: underestimating concrete volume due to irregular formwork or slab thickness variations. Impact: shortages lead to rushed orders, plus 10–20% cost premium. Example: assuming a uniform slab thickness when actual thickness varies, e.g., 200 mm versus 250 mm. 2. Rebar overlap and wastage errors. Mistake: not accounting for lap splices, typically 40–50x rebar diameter. Impact: extra 5–10% steel ordered unnecessarily. Example: 100 m of rebar may require 105 m after accounting for overlaps. 3. Unit conversion errors. Mistake: mixing metric, kg, m superscript 3, and imperial, lbs, foot superscript 3, units. Impact: major discrepancies, e.g., 1 ton is not equal to 1 metric ton equals 1.102 short tons. B. Sustainable housing, timber and recycled materials. 1. Moisture and shrinkage in timber. Mistake: not accounting for wood shrinkage, 3–5% in CLT. Impact: gaps in joints or misaligned structures. 2. Recycled material inconsistencies. Mistake: assuming recycled steel/concrete has identical strength to virgin materials. Impact: structural weaknesses if not properly tested. 3. Incorrect waste factor assumptions. Mistake: assuming 5% waste when actual wastage is 10–15% for recycled materials. 2. Calibration and error correction. A. Calibration techniques. 1. Digital measurement tools, laser scanners and BIM software reduce manual errors. Example: using 3D modeling to detect rebar clashes before pouring concrete. 2. Scale and sensor calibration, regular calibration of batching plants, concrete, and weighbridges, steel. Example, a 1% error in a 50-ton steel order equals plus or minus 500 kg discrepancy. B. Error correction methods. 1. Real-time adjustments, RFID tracking for steel deliveries to match actual versus estimated quantities. Example, detecting a 2-ton shortfall in real time and adjusting orders. 2. Statistical waste forecasting, historical data analysis to refine waste factors, e.g., 8% instead of 5%. 3. Post-construction audits, comparing as-built material use versus estimates to improve future accuracy. Summary table, errors and solutions. Error type: high-rise impact, sustainable housing impact correction method, volume miscalculation, concrete shortages, plus 20% cost, timber gaps, BIM modeling, 3D scanning, unit confusion, incorrect steel orders, misorided recycled materials, standardized metric / imperial checks, unaccounted waste. Excess steel, 5-10%, higher timber wastage, historical data analysis, material strength assumption over design, safety risk, structural weaknesses, lab testing of recycled materials. Key takeaway: high rises suffer from bulk measurement errors, steel / concrete tons. Sustainable housing faces precision challenges, timber shrinkage, recycled content variability. Solution: combine digital tools, BIM, sensors, with empirical data to minimize errors. Would you like a deeper dive into calibration standards, e.g., ISO 9001 for material testing? Part B, Sustainability and Innovation. 19. Eco-friendly construction materials: a low-carbon concrete and recycled metals. 1. Low-carbon concrete, key innovations: geopolymer concrete, uses industrial waste, fly ash, slag, instead of Portland cement, reduces CO by 40–80%. Carbon cure, injects CO into wet concrete, mineralizing it and reducing emissions. Measurement: embodied carbon measured in kg/CO/m superscript 3, traditional concrete, 400 kg/m superscript 3 versus geopolymer, 150 kg/m superscript 3. 2. Recycled metals, key innovations: recycled steel, saves 75% energy versus virgin steel, measured by percent recycled content, e.g., 90% in some beams. Aluminum reuse, post-consumer scrap, reduces emissions by 95%. Measurement: EPD, Environmental Product Declaration, tracks life cycle impacts. B. Measuring embodied carbon and life cycle analysis, LCA, embodied carbon calculation, scope, covers extraction, manufacturing, transport, and construction, A1 A5 stages in N 15978. Tools: Tally, BIM integrated LCA, one-click LCA. Example: a steel-framed building may emit 1,200 kg CO/m superscript 2 versus timbers 200 kg CO/m superscript 2-20. Emerging materials and technologies: A. Self-healing concrete and smart materials. 1. Self-healing concrete, how it works: microbial, bacteria, e.g., Bacillus pseudofermis, precipitate calcite to seal cracks. Polymer-based, capsules release epoxy when cracked. Measurement: durability increase, reduces maintenance by 50%, measured in crack width healing, e.g., 0.3 mm 0 mm. 2. Smart materials, shape memory alloys, steel that remembers form, used in seismic zones. Phase change materials, PCMs regulate temps, reducing HVAC loads by 15–20%. B. Nanotechnology in construction. 1. Nano-enhanced materials, graphene reinforced concrete, 2x stronger, 30% lighter, measured in MPa strength. Nanosilica coatings, waterproofing with 100 nm particle penetration. 2. Applications: Self-cleaning glass, TiO nanoparticles break down dirt, measured in % light transmittance. Carbon nanotubes, CNTs strengthen steel while reducing weight, 1% CNTs equals 10x tensile strength. Sustainability versus innovation comparison aspect eco-friendly materials emerging tech focus reducing CO, LCA driven, performance enhancement key metric kg/CO/m superscript 3, embodied carbon, MPa, crack healing, % efficiency adoption barrier higher upfront cost scalability and long-term testing example geopolymer concrete, 150 kg CO/m superscript 3, self-healing concrete, 0 mm. Cracks, future outlook, regulations, EU's carbon border tax will push low-carbon materials. AI integration, machine learning optimizes material mixes, e.g., AI-designed concrete. Would you like case studies on net zero buildings using these materials?